Okay, good morning, everybody. So, we had the mechanical engineering class, electrical engineering, now it's chemical engineering. So, hope you pay attention. I'll talk about some of the activities in what we call as a process systems engineering group in chemical engineering department, where we work towards digital initiatives in the process industry. So, we have a set of faculty members. So, they are listed over here. So, about 8 faculty members working in this area and broadly related to process manufacturing. There are many others who look at, for example, materials, catalysts. Those I have not put here, because that's not my domain. So, you need to see Sachin Patwardhan, who is our dean, is here, and this is me. So, what is the aim of the PSC group? So, broadly speaking, our aim is to work towards operational excellence in manufacturing. So, towards that, we want to essentially develop and deploy improved production practices to ensure safety, optimality, compliance with user specifications, with various metrics of sustainability. And towards this end, we use a lot of ideas from control theory, optimization, probability statistics, machine learning and AI. What Prof. Sachin mentioned, like many of these control theory, optimization, probability statistics have been in use for a long time. Even machine learning, AI have been in use in process domain, in process control domain for a long time. But now, of course, they are coming in with better versions, newer avatars. And I would also like to point out this key aspect, which is missing when people talk of machine learning. Sometimes they think of it like a black box. You throw in data and you get something out. That is still not possible. I don't know if it will be ever possible. So, but this is where we also bring in domain knowledge, where we would like to differentiate ourselves from, let's say, machine learning specialists, or let's say pure data scientists. And we demonstrate our ideas using simulation examples, using lab scale experimental setups, or also wherever possible on real industrial processes. So, PSC group activities, we look at industrial applications, so plant-wide dynamical systems, how they operate, we model them, look at their performance. Methods and algorithms, we look at both linear, nonlinear processes, fast optimization, computations, real-time operations. Okay. And for that, we use models of various types. So, I'll have probably a bit more to say in the next couple of slides. So, if you look at the methods and algorithms, so these are some of the techniques where we have the expertise. So, these are the toolkit that we have. So, all geared towards process design and operations. So, control relevant modeling, optimal sensor network design, simulators, process control, advanced process controls, optimization, state estimation methods, and the like. Okay, and now of course, AI ML is there in all these approaches. So, this is integrated. I mean, we really don't see any difference as such. So, as far as process operations is concerned, this is a typical hierarchy of operations, you can say. At the lowest level, you have the plant, where you have your actuators, and you have regulatory control, supervisory control, optimization, site-wide optimization, and so on. So, we work at all these layers in operation, okay? And also some related design activities. If I have to operate well, I need to measure the right set of variables. So, we look at some of those areas as well, and we look at some process design. So, both process operation and related design activities as well as process design is what we look at. Now, ultimately, see, any activity you do, you want to know this digital transformation or any other activity, ultimately it's about modeling, right? So, a lot of effort in any such activity goes into developing models. So, we work with different types of models, and there is a saying in statistics. So, George Box is a famous statistician. He had said this: all models are wrong, but some are useful. Okay? So, that is what we also believe in. Depending on the application, you choose the right model at the right level of details or granularity. It's never going to be a perfect model, but it should be appropriate for your application. Okay? So, digitalization for us, the theme of today's workshop, it essentially means that you develop. So, now this is the term people use, digital twin. I don't know what in the previous slide said model cannot be perfect, but people say it's a digital twin. So let's use this terminology. So there's a kid looking at the mirror and seeing his reflection. We know that digital twin, really you cannot have a perfect capture of reality under all operating conditions, but for certain conditions maybe you can do that. So a physics based model. So for us, digitalization means you develop these digital twins using variety of these modeling paradigms. You could have first principles physics based models, you have data driven models, or what we call as a gray box model, some combination. So use the right model and then use the developed and validated models for design, training, real-time operational activities, a bunch of activities I talked about. And a key aspect, some of the tools that we look at, for example, state estimation, parameter estimation, adaptive control, fault tolerant control. Also, so there is a big challenge in using these models as to how to maintain these models. You develop a model now, 2 months down the line, it doesn't work, it doesn't mimic your process. You have to continuously update your model. So we have a lot of research going in that area of adapting your models and your control methods. So if you look at, so what I'll show in the next few slides is just give you a glimpse of some of the activities, some of the applications, either on some experimental setup or maybe sometimes simulation or industrial setups, where different types of models have been used. So these are dynamic or what you can say is physics based model, first principles based model. Okay, so these are just some representative applications. So this is a DW sim based simulator development is one activity which is going on in our department. So this is an open source dynamic simulation exercise is being conducted. So Professor Kannan is leading that. So there it has been tried on various processes. It's modular in nature, and it's also being right now customized for refinery. So we have the person who is leading it from the industry side. This one activity. This is another illustration of a first principles dynamic model. So Professor Sharad and me, we worked on this, and we are still working on this. So this is a plant-wide dynamic model developed for a hybrid solar thermal 1 megawatt electrical power plant. So it's a dynamic simulator validated on plant data, and now using this type of plant. So what you see here is during daytime, these are daytime operations. Now you can actually simulate startup, shutdown, diurnal variations, do a lot of what if analysis, your different operating strategies, design ideas, you can try out plant-wide control analysis. Okay, and this is the original plant did not have nighttime operation capabilities, so some proposed designs if you want to enhance that capability. So now you have a simulator, you can do all these exercises. So using some additional salt storage, you can operate the plant at night. This is another activity by Professor Gudi and Professor Sharad, where some scheduling of renewables is being studied along with reformer integrated proton exchange membrane, fuel cell and energy storage. So again, they have a dynamic model of the fuel cell, and the energy generated has been integrated so in a scheduling framework along with some other sources. Professor Sujit, an illustration of optimal operation in batch distillation. Again, dynamic models are developed for this, and you can now try to optimize some profit that you want to generate while meeting the product specifications, and you can come up with optimal operation. So all these are in some sense in you can say modeling terminology. These are like first principles models have been used in various approaches. Okay. We also look at data driven models. So regression is a very widely used modeling technique in various forms. So time series analysis, a lot of expertise we have in looking at time series models. Decision trees, random forest, all the now these models which are available with machine learning, AI, and more principal component analysis based models, and so on. So a distinguishing common feature, as I said, compared to what I would say is other pure data scientists or somebody who's working purely in AI, is that we try to utilize as much prior knowledge that you have. So really the models are not completely black box in them. Whatever information you have about the process, and that's really the strength be working in a domain, being chemical engineering, mechanical engineering, you have some information, some knowledge about that. You exploit that prior knowledge to the extent possible. You have the right set of variables which you use for modeling. So ultimately, what I would think is what we work on is gray box models and not just pure black box models. So these are now some, so again, some examples of those gray box or machine learning motivated models on different applications. So this is Professor Goody's soft sensor, where you want to predict certain quality variable which is hard to measure, but it's important for your online control. So this, I think maybe there is a talk in the afternoon, so I'll skip this, but this is some activity which is developed with the company. This is Professor Sharad's another soft sensor approach to predict the ASTM 95% temperature of kerosene, and again the lab measurements are hard to come by, and they've built a neural network model, but again the neural network model was or exploited the first principles understanding. It was not a complete black box, so it was like a two-stage neural network which finally worked, and this was implemented in a large refinery DCS. This is an activity, a soft sensor again. So soft sensor, the idea is you are trying to predict some variable which you are not measuring. Okay, so you are building a software sensor, computer based sensor. This is another illustration in a dynamical setting. Again, some case study, but applied on some industrial data. What you see here is a lab setup, implementation on lab setup because of confidentiality reasons. This is some important variable, some leak which is some parameter which is important to you, some fault which is occurring. You really cannot observe this, cannot measure this, but you can still estimate this using the methods that we developed and using other measurements. This is some other ideas. So using reinforcement learning. So this is now people call it a model-free approach for tuning your controllers. So an implementation, a schematic of that. And also we have a lot of expertise in using dynamic models for model predictive control applied for nonlinear processes. And Professor Sharad's one application, they used ANN model, artificial neural network models for model predictive control on this dynamical system. So this is actually a challenge problem in literature, which is called as the Tennessee Eastman problem. So many times in our community, if you work on some research area and you show on this problem, this is considered as like the gold standard that if it works on this problem. So on this problem, again, they trained a radial basis function feed-forward neural network. So it's a machine learning model, and then applied model predictive control on it to control various variables. Professor Sachin is also an expert in model predictive control. Some of his work, what he does is also the challenge I said in modeling in systems is you can develop models, but you have to keep updating them. That's the biggest challenge. So Professor Sachin looks at schemes where while you are controlling, you are also updating your model. So dual adaptive schemes. So we meet the control objectives, update models as well. He also looks at fault tolerant schemes where if there is some abnormality which occurs in your process, you recognize that abnormality, updates your models accordingly, and reschedule your controllers. Okay. This is another application of sensor network monitoring. So this is some work we did with NPCIL and BARC. So we looked at essentially a set of detectors which are used in a nuclear reactor to measure the flux, and there are hundreds of such sensors, and the aim was to monitor those sensors because those are critical for the operation of the nuclear reactor. So we used some clustering and principal component analysis based models to develop models and then continuously update them using some recursive ideas to update them in time. And using those models, you could build a system which could detect that there is a problem with the sensor or not. So the difference here is like the measured value and what your model predicts, and it tells you that there is some issue with a particular sensor. There's another exercise, again data driven model using principal component analysis and and slow feature analysis approaches, um, where, so this another interesting area is where you want to do prognosis. So not just know that a failure has happened, but predict that a failure is going to happen. So in this simulation based case study, we could predict the off spec product well in advance, that okay, now something has happened, little later down the line you are going to get off spec product, so you better take corrective action now. So this Professor Goody's work is just an illustration of what people are now, what we are calling as physics informed neural networks, where while training a black box model, you try to take it to a direction where it also incorporates some first principles information, and that they have used for in a tubular reactor for optimal temperature trajectory. Maybe I skip some of these slides. So these are some of the now the research areas that we do. So we work a lot, in methods and algorithms in MPC. So this is some scheme for fast optimization. When you deploy these advanced process control schemes, you don't have you can't do a lot of processing. So how do you do fast optimization? Professor Sujit looks at some distributed control, again advanced control, so that you can scale it to larger processes. Professor Goodies as also looks at control loop performance activities, and is applied to some real systems. Sensor placement, I work in this. So this is some illustration, just a schematic, that optimal choice of variables in a water distribution network. Yeah, this is optimal. Maybe I can skip this slide. Some recent activity we have started is, so whatever I presented so far was on process. This is on digitalization of documents. So you have a piping PNID, okay, piping and instrumentation a diagram, and it is, you have a hard copy or an image, you want to scan it, and you really want to not just scan it, you want to extract what information is there. So you really digitize it, and then once you have digitized it, now you can process it. You can do, for example, how the various units are connected, how information flows, and so on. So that is really, you can get a smart PNID. So to summarize, there are significant activities in various areas of process design, process operations in the group, unit level as well as network or plant level. So the group here is strong in modeling, which is really the heart of digitalization. Ultimately, it's about what models you have, and for that we use various data analytics, control, and optimization tools. Thank you.